All right, now let's kind of shift. So I want to talk about something called an electroscope. You may have seen this in a science class that you've had. So this is just a glass beaker. This is a conductor. It's a piece of metal. This is metal. It goes through the cork and everything, stopper, metal, metal. And these are just like little sheets of metal foil. And so you use this to demonstrate charge. And so if you were to touch something, like if you were to, let's say this thing had a lot of negative, let's say this thing had a lot of negative charge, and I touch it, then the negative charge will be transferred to this. And then, since this is all a conductor, it's all metal, right? The negative charge will move down here and get on these metal these foils, these leaves. And if this is negative and this is negative, remember, like charges repel. So the leaves will just go like that. So that's just, you know, a nice little experiment that you've probably, hopefully seen a long time ago. So that's electroscope. Here's the same thing, all right? So again, so somehow you charge this negatively. These are all conductors, and so the electrons flow. Initially, the leaves are like this. When they both get charged, they repel, so they go like that. So that's a charged electroscope, all right? Charged electroscope. All right. Okay. Now this is called the photoelectric effect, which I told you I was going to describe in gory detail, but you had to learn all that other stuff first to understand this. I'm right, sorry. So here is a charged electroscope, right? It's charged because the leaves are, you know, like that, right? And what you do to this charged electroscope is you shine light at it. So for example, ultraviolet light. So you shine ultraviolet light at it, and I'll explain later why can't it just be any kind of light? I'll get to that. So you shine light on it, and look what happens. The electrons get emitted, right? All the electrons are emitted. And then, since this no longer has a charge, you know, you had these charged leaves. Well, if all the charge is gone, then the leaves go back like that. By the way, this is kind of a strange term. So they call these things photoelectrons. They're just electrons, okay? But they're electrons that have been emitted via the photoelectric effect. So that's why they call them photoelectrons. But an electron is an electron, so they're just electrons. So don't get worried about that. Okay, now here's the important thing. Look, wait a second. You know, that last hour or whatever, half hour, you know, when we were ejecting electrons from the vacuum tube, how did we do that? We did that by heating up the metal cathode, right? We heated up the cathode, so the electrons had a lot of thermal energy, so they could exceed the work function, and then therefore escape. This has nothing to do with heating it up. We're shining light. Okay, all we're doing is shining light on this. And it's UV light. Okay, it's not like X-rays or something. So we're just shining light on this, but somehow we're emitting the photons. So something's going on, you know? Something's going on that's very, very different. And that really confused people for a long, long time. All right, so there you go. So that's the photoelectric effect, all right? You shine light on something that's charged, and the electrons are emitted. And it has nothing to do with increasing the temperature, okay? Okay, so let's talk about the experiment. Oh, let's see. Okay, I want to show you all the. Okay, so here's like a photoelectric effect experiment. So here's our vacuum tube again, right? Here's the cathode. Here's the anode. Okay, now we can't change the temperature. Now we're just going to shine light on it. All right. You know, that might increase temperature a little, but certainly not enough to do this. So the temperature has nothing to do with it. Okay, you'll see. Okay, window. There's the battery. This thing measures the current. So let's go through it. So the photoelectrons that are emitted from this form a current between the cathode and the anode. So I have a complete circuit. So there's the battery. So the potential difference, the voltage, can be changed, can be reversed, whatever you want to do, just like last time. The current can be measured, while the potential difference can be measured. The frequency of light can be measured. The light intensity, if it's bright or not, or if it's dim, all that stuff can be measured. Okay, so there's like a modern photoelectric experiment. So here's the results. Number one, if you increase the light intensity, you increase the current, but it has nothing to do with V-stop. Now hold it. You have to understand this. Okay, wait a second. So the fact that V-stop doesn't change means that the kinetic energy of the electrons doesn't change, right? But look at, you get a higher current. Well, why? Okay, so what does light intensity mean? It just means you're getting more photons, right? What's the difference between a bright light and a dim light? A dim light, you're not getting very many photons per second, but with an intense light, you're getting lots and lots of photons per second. So it's just the number of photons per second that increases, right? That's what intensity is, just the number of photons per second. Okay, so you increase the intensity, you get more electrons, but it has nothing to do with the kinetic energy. So let's just might as well read this thing, right? A more intense light causes a larger current because you have more photons per second emitted. Again, no current flows if the voltage is less than minus V-stop. The stopping potential is the same for weak light, intense light, whatever. So the intensity of the light has nothing to do with the kinetic energy of the electrons. And just like before, the current is independent of delta V after a certain, right, if it's positive. Okay, now here's the question. Does this agree or disagree with classical explanation? So what do you think? Well, it completely disagrees, right? Completely disagrees, because if you really, really increase the intensity, you're going to increase the temperature of the metal somewhat, right? Right? And so, you're going to increase the thermal energy, which means you're going to increase the kinetic energy. But that's not the case. That's not the case at all, right? So something's weird, right? Something is definitely weird. Okay, number two, and this is the big one. There's a threshold frequency of light that depends on the cathode material. All right, what does that mean? This is what it means. So remember, light acts like a wave. It has a frequency, right? So what this says is that there's a threshold, a certain value of the frequency where I don't care how intense the light is, nothing, no current, no electrons will be emitted if the frequency of that light is less than this threshold. So this could be the brightest light you could imagine, but if the frequency of that bright light is less than this threshold, no electrons are emitted, so there's no current. On the other hand, I don't care, look, no matter how weak the light, there's going to be electrons emitted if the frequency of this light is greater than the threshold, right? So everything depends on the frequency of the light. If the frequency of the light is less than the threshold, no electrons are emitted. If the frequency of the light is greater than the threshold, electrons. The intensity is irrelevant. Everything depends on the frequency. That's what they mean by threshold frequency. Okay, does that agree with or disagree with classical? Completely disagrees, right? Classical physics had nothing to do with frequency of light. That's completely ridiculous. Okay, regardless of the light intensity, the current appears instantly, no delay. Now that disagrees with classical, because remember, classical physics, you've got to heat up that cathode. It takes a while to get it hot enough so that the thermal energy exceeds the work function. With a photoelectric effect, if the frequency of the light exceeds the threshold, bingo, there's no delay. The electrons are just emitted. Bang. Okay, so what is going on? All of these experimental results completely disagree with the classical theory. And so that really was very perplexing to the people at the time. So guess who saved the day? I already told you in chapter 36. Who got the Nobel Prize for quantum mechanics for photoelectric effect? Einstein. Remember, he thought he should have got it for relativity, but he didn't, and he was really ticked off. Okay, so Einstein figured out the photoelectric effect, got the Nobel Prize for it. And this is what he said. He said, light is not continuous. It actually comes in chunks, okay? It comes in chunks. It comes in, let's get the term on, it comes in discrete quanta of energy. And he gave it a name. And you know what the name is? A photon. Okay? Discrete quanta of energy. I like to say light comes in chunks. All right? Now, every photon or every chunk or every discrete quanta of energy has energy E equals hf. So you can see there's that frequency dependence, right? That energy is related to frequency. Now hold it, energy equals hf. But we know that, remember, F equals ma for waves, velocity equals f lambda, but now we're talking about the speed of light. We're talking about light, so we have this, right? So therefore F equals c over lambda. So we can also say this is hc over lambda. Now, come on, think about this. We're talking about light coming in chunks, right? So you have a chunk, some people say that a photon is a particle of light. So we have a chunk of something, sort of like a particle, but it has a wavelength. And that's kind of weird, right? So it's sort of like light is a particle and a wave. Now remember when we talked about waves, I showed you that one slide. It had a picture of a man in a suit and he had his fingers crossed or something like that. And I told you how to explain that. Well, now's the time. So Einstein is saying that light acts like a particle and a wave. Now that's weird, because what do we keep saying? What do we say when we learned waves? We said that waves and particles are completely different, right? Waves and particles are completely different. Well, now we have light acting like a particle and a wave. Weird. Okay, by the way, H, this is called Planck's constant. Planck's constant. So Planck is a physicist, Nobel Prize winning physicist. This is a super, super, super tiny number. And that's one reason why we don't notice that light comes in chunks, because this energy is so incredibly small for most types of light, it's very difficult to see. Okay, so this is like fundamental, this is super important equation. You want to remember that or write it down. So for light, this is light, H equals hf, which is hc over lambda. Super incredibly important. We'll use it again and again and again. All right, so Einstein said light comes in chunks. That's the energy, that's the frequency and all that. And he also said that each photon travels in a straight line at the speed of light. Now, what does that kind of imply? Photons going in a straight line. It's like the ray theory, right? So, my gosh, wave, particle, travels in a straight line. All right. The chunks cannot be divided. So there's no such thing as a half a photon or a quarter of a photon or 1.5 photons. It's like a piece of dirt. I mean, if you have a piece of dirt, do you say there's a half a piece of dirt? No, you say there's a piece of dirt, right? Okay. So it's the same thing. And when the photons hit the cathode, they're either absorbed or they're not. You can't say like half is absorbed and half isn't, right? It's all or nothing. Same thing with emitted, right? So a photon is either absorbed or there isn't absorbed. It's an all or nothing thing. And like a substance, if you heat up a substance and it emits photons, you can't emit like 1.5 photons because, again, there's no such thing, right? You either absorb a photon or 2 photons or 3 photons, or you emit 1 photon, 2 photons, whatever. No such thing as a fractional photon. Okay? Now, the energy of 1 photon is delivered to 1 electron. So that means that when the photon hits the metal cathode, that all of that photon's energy is absorbed by the one electron. Okay, there it is. So that's what Einstein said. Okay, and here's an analogy. I don't know if you might not like it, but some people think it's a pretty good analogy. So this is the raindrop analogy. So think of every raindrop represents a photon, and every raindrop has a definite size, right? And that's supposed to represent like the energy. Like every photon has a certain energy. And the intensity of the rain is determined by the number of drops per second, right? If it's really pouring, you're getting a lot of raindrops per second. Well, the intensity of light is determined by the number of photons per second. Just the number, For high intensities, if you have really, really pouring down rain, it sounds, you don't really hear dit, 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 right? You just hear a continuous sound. Well, it's just very similar. If you have super, super bright light, you don't just see like one photon, another photon, a photon. You just see light, right? You just see the bright thing. And the energy of the rain has nothing to do with the intensity, right? Because again, intensity is just numbers per second. So the energy of the raindrop has nothing to do with if it's pouring or if it's not pouring. So that's the same thing with a photon, right? The energy of a photon has nothing to do with intensity. Intensity is just numbers per second. And the raindrops fall in pretty much straight lines, except there's a lot of wind, we don't care about that. And photons travel in straight lines. So there's just an analogy. Okay, now let's see Einstein. How does Einstein's explanation explain the results, right? How does Einstein's explanation explain the data? I mean, that's what we want to see. Okay, so let's see. All right, so let's see how Einstein's explanation explains the data, whereas the classical physics has no hope at all in explaining the data. All right. Let's see. Okay. Number one, increasing the light intensity increases the current. Well, that's simple. When you increase the light intensity, you're just getting more photons per second, right? Well, every photon, if the energy is enough, right, if the frequency is exceeding the threshold, emits an electron. So if you have more photons per second, you can have more electrons per second. In other words, you can have a greater current. Okay, so that's fine. So that explains that. I'll get to that later, right? I just want to talk about this. All right, so increasing the light intensity means you get more photons, so you get more electrons. That's fine. Okay, number two, there's a threshold frequency that depends on the cathode. Well, that's easy, right? I mean, that's just this, So the energy, okay, so an electron is emitted if the energy of the electron, well, if the energy, okay, the light energy has to be greater than the work function. Because remember, the light energy is transferred to the electron. So if the electron's energy exceeds the work function, it's emitted. So it's basically this. So the energy of the photon or the light, whatever you want to call it, all right? Now that equals the energy of the photon, okay? And that's equal to hf, right? That's Einstein, hf. And all that energy gets transferred to the electron. So that's the energy of the electron. And that has to exceed the work function for the electron to be emitted, right? Right? So what does that really say? That says that HF has to be greater than E0, right? And what is HF? Now remember, let's say that okay, F0 is like the threshold frequency, right? So if the H times the threshold frequency, that has to be greater than that for the electron to be emitted. So that means that the F0 equals E0 over H. Okay? So in other words, if the frequency of the electron is less than the threshold, cough! It's not going to work. If this is greater than the threshold, it's going to work. All right? That's really how it is. So this should really be a greater than, yeah, right? Okay? So the threshold frequency, well, the frequency of the photon has to be greater than the work function divided by h. So they usually just say that the threshold frequency equals E0 over h, all right? That's what they usually say. But again, remember, the frequency has to be greater than that for the electron to be emitted. So this equation, that the energy of the photon equals hf, that explains the whole threshold frequency business, right? There's either enough energy or there isn't enough energy. It's as simple as that. Okay, the next one. Okay, this one, I mean, again, if you have the right frequency, the electron absorbs the energy and it's emitted. You don't have to wait for the cathode to get hotter and hotter and hotter. There's none of that stuff. So it just happens instantly. Okay, now we want to talk about that V-stop. Okay, and now we're going to discuss an equation which is like the fundamental equation for the photoelectric effect, so it's a big deal. All right, let's go over here. Okay, so this is supposed to be V-stop, sorry. So, using this, we have V-stop equals K max over E. All right, that's cool. Now, what is K max? Well, it's just the energy of the electron, minus the work function, right? Over E. All right? And what's the energy of the electron? The energy of the electron equals the energy of the photon. What's the energy of the photon? Well, let me write that. E photon minus E0 over E. What's the energy of the photon? HF minus E0 over E. Okay, now, what's E0? I just told you, right? So HF minus HF0. Again, F0 is a threshold over E. And now look at, that's a constant, that's a constant, the threshold frequency is a constant, depends on the metal, that's a constant. So this is really the only variable is F, you know. So let's write this differently. So we want to write it like a line. Remember, this is V-stop. So it's H over E, which is a constant, right? So times the variable F minus HF0 over E. Now, look, this is a straight line. V stop equals constant times F minus constant. So F is the slope, right? So Einstein made a prediction. He made a prediction that the V stop equation should be aligned with the frequency as the variable. So there's the equation, right? V stop equals H over E, F minus HF0 over E. So you straight line, you plot it, you see if it agrees with the data. It does, okay? So the fact that the data agreed with this equation that Einstein came up with, that was like super important because it verified that what he was saying was correct. So this is a big deal, super big deal. Okay, finally you get to answer a question. So a xenon arc lamp is covered with a filter that only transmits light 400 nanometers with the wavelength. When the transmitted light strikes a metal surface, a stream of electrons emerges from the metal. So in other words, the frequency of the light, that's, you know, so in other words, the 400 nanometer wavelength, that light, the frequency exceeded the threshold frequency. So when the light hits the metal surface, a stream of electrons emerges from the metal. Okay, if the intensity of the light striking the surface is doubled, what happens? So this is just this is basically a question of what we just discussed. So pause your video and figure it out. Okay, so all we're doing is increasing the intensity. So we already know that the photons have enough energy to emit the electrons, right? The frequency is greater than the threshold frequency. So that's fine, but now we're increasing the intensity. That just means we're getting more photons per second. Well, if the photons are already capable of emitting the electrons, we're just going to get more electrons per second, right? So what's the answer? But wait a second, hold it. If we increase the intensity, does that have anything to do with the energy of the electrons? No, not at all, right? There's no intensity. You see any intensity anywhere here? And remember, intensity is just the number of photons per second. So the answer is 1. All we're going to get more electrons. They're not going to be more energetic. It's just going to be more electrons. Intensity has nothing to do with energy. Here's another one. Okay, a xenon arc lamp is covered with a filter. It only transmits 400 nanometer wavelength light. When the transmitted light strikes the metal surface, a stream of electrons emerges. So we're exceeding the threshold frequency. Then you replace the filter. The filter is then replaced with one transmitting at 300 nanometers. Okay, so hold it. Just look, think about it. If the wavelengths are getting smaller, what happens to the energy? It's going to get larger, right? Or, here's another way to think about it. You can say C equals F lambda. So if this gets smaller, this gets larger. Well, okay, I think I just gave the answer away. All right. The filter is then replaced with one transmitted at 300 nanometers. The lamp adjusted so that the intensity of the light striking the same surface is the same as it was before. With 300 nanometer light, what's going to happen? So you have the same intensity, but they have greater energy because the frequency is increased. So what does that mean? So pause your video and figure it out. Okay, we're not going to get more electrons because we didn't increase the intensity, but the electrons that are going to be emitted are going to have more energy, right? Because we increased the energy of the light. So V stop is going to increase. All right? Okay, so that should make pretty good sense. Okay, let's just a little review. Yeah. So there it is. Let's review again, okay? Let's review all of the models of light that we've talked about. So this is the photoelectric effect, right? So this is the photon model of light. The photon model of light says light comes in chunks. And the energy of each chunk, again, a chunk is a photon. Energy of each chunk is HF. And you do the photoelectric experiment, you come up with that equation, you get this data, everything works. Right? So the photon model of light accounts for the photoelectric effect. Okay, now let's talk more about these chunks. Well, if you have really low intensity light, hitting a screen, you can actually see the little pieces of light, right? You can see the specks of light. All right, so this is low intensity of light. Doesn't this imply that light comes in chunks? Yeah, it sure does. In the real world, there's something called a photomultiplier tube. Photomultiplier tubes, you can use them to detect single photons. I have one in the McKay building. I'm doing an experiment, and I have a photomultiplier tube. It detects single photons. These photomultiplier tubes, believe it or not, they use the photoelectric effect. So this is the photomultiplier tube, right, in glass. And here's a metal, and light hits this metal, and an electron is ejected. And then you just use different voltages to multiply the number of photons. Because, we don't have the electronics to be able to detect a single electron. So you have to multiply them until you get gazillions of electrons, and then you can detect that as a signal, right? So all I'm saying is that there's evidence, real evidence for the photoelectric effect. It works, okay? And that means that the photon model of light is correct. It works. we also have the wave theory of light. Remember the double slit with light? You do the double slit with light, and you know, Isaac Newton would have thought there would have been a bright spot here and a bright spot here, and that's it, right? But yet you do the experiment, and oh my gosh, you know, the light acts like a wave, and you get places where there's constructive interference and places where there's destructive interference. So here, let's do the double slit experiment. So we start off with very, very dim light, and we just see those photons, you know. Then we just wait, we just keep doing it, waiting, 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 and now you're beginning to see a pattern, right? Keep waiting, oh my gosh. So destructive interference, constructive interference, destructive interference. Keep waiting, and you get that. So there's the wave theory of light. It works, you know? I mean, what can you say? Okay, here's something neat. I don't remember if I showed you this before. This is a really cool experiment. This is the single photon experiment. So here I have a molecule. It's going to emit one photon, okay? One photon. So here's a mirror, path 1, path 2, and then you know, they reflect, and you know, if they constructively interfere, here you can see that. If they destructively interfere, you can see that, right? You can change the paths to make it constructive or destructively interfere. But wait a second, there's one photon. How can you have interference from one photon, right? I mean, because the photon acts like a wave, so some of it goes this way, some of it goes that way. Let's read it. The light from a single photon emission in source S travels over two widely separated paths. So this is one photon acting like a wave. So it travels over two widely separated paths and interferes with itself at detector D after being recombined by the beam splitter. So this is real data. This is a real experiment. You can read about it if you want. So that's the wave theory of light. It works, all right? It works. Okay, so we started off, you know, this is like light acts like a particle, right? Photoelectric effect, light acts like a particle. There's a particle, right? Single photons are detected by PMTs. Particle. Particle. Then we have wave, right? Wave. And then we have the photon. So, which is related to the, well, whatever. What's the ray? You know, the ray is optics, right? The ray is optics. So this is like the particle model, the photon model. Light is made out of massless photons, travels straight lines, speed of light. Energy of a photon equals hf, hc over lambda. Don't forget that. The superposition of a large number of photons has the characteristics of a classical wave, right? You have a ton of photons, you see like the wave properties. Now, this is something which is all fake, but people talk about it. So, photons are sometimes approximated or visualized as a wave packet, right? This is just a classical model, you know. So you're just imagining that this is like a wave, but it's different amplitudes, you know. And so this acts like a photon. It's false, right? But we're going to talk about it later on. So the only reason I'm showing you now, I just want you to remember it, okay? This is a classical model of a photon. It's not right, but we'll use it later on. And that's a good place to stop. Thank you very much. Finally.